If you turn this video off, then please tell me the reason so that I can improve. Otherwise, hi America, I am trying to learn physics today, how light behaves, and after we've done it, we're going to do body center training. And if you participate in the body center training, then it's at your own risk. And this is the second part to light. Now, light as waves. It is now known that light is just a part of a much wider spectrum, most of which does not affect human senses directly. They said that there's a lot of radiation differences, and light is just a small part of it visible by the human eye. Collectively, the different forms of radiation included in this spectrum are known as electromagnetic radiation. They all travel at the same speed in empty space, the speed which has been measured at 300 million meters per second, or 300,000 kilometers per second. This is known as the speed of light, but is also the speed of any form of electromagnetic radiation. Okay, they are saying not just the visible part of the whole electromagnetic radiation travels at the speed of light, but also the other things. Forms, another thing, they're saying light is a form of electromagnetic radiation. They are saying that here right now. This is known as the speed of light, but is also the speed of any form of electromagnetic radiation. It is known that the light is just a part of a much wider spectrum, most of which does not affect human senses directly. Collectively, the different forms of radiation included in this spectrum are known as electromagnetic radiation. Okay, they're saying that whole thing is electromagnetic radiation, and light is a part of a big spectrum of electromagnetic radiation. And all on this electromagnetic radiation, including light, moves or travels at the speed of light. I hope it is correct. So that is what I understand from that, and that would be something new. Forms of the radiation differ from each other in their wavelengths. Visible light has a wavelength of over 7/10 millionths of a meter. For red light, and of about half that figure for blue. Okay, light has a size of around 7/10 millionth. So not a millionth of a meter, but a 10 millionth of a meter, so very close, and 7 of them. 7/10 millionth, so I could say 1 millionth. 1 millionth. 1 millionth of a meter has light as a begins. So that would be 1 meter, and that would be half a meter, and that would be 1/100th of a meter. 1 centimeter is 1/100th of a meter. That is a full meter, and that is 1/100th of a meter. And now if we have a thousandth of a meter, that would be a millimeter, with the size of a nail. 1 millimeter, that would be a thousandth of a millimeter. And when we have 10,000th, 100,000th, and 1 millionth of a millimeter would be the size of light. So very, very small. 1 millionth of a millimeter is the red light, and blue light is the half of it. And there we have it. Blue light has another length. Blue light itself has just a half of a millionth of a millimeter, or 0.3. 0.3 of a millionth millimeter, and red light has 0.7 millionth of a meter. We could say it differently. A meter, that would be a hundredth, a thousandth of a millimeter. Let's say centimeter. That would be a hundredth. That would be a thousandth of a centimeter. Is that easier? I think that's easier. A millionth of a meter is the same as a 10,000th. A 10,000th of a centimeter, I think. Maybe. I think that would be easier to remember. We're going to come back later to that. And blue light has just a half of a size. Above and below light in the electromagnetic spectrum, the wavelengths stretch from a kilometer or more for long-wave radio waves to less than 1 millionth of a meter for gamma rays. Okay. Okay, the whole electromagnetic spectrum has somewhere in the middle light, visible light. The red light is here, half a million of meter, and the blue light here, or full million, 0.7, and the blue light with 0.3 million of a meter size. But we're having here the radio waves. The radio waves, they are over a kilometer long, so very, very long. What you can run in 5 minutes, or 3 minutes, depending. So very long. And then we have light in the middle, just a million of a meter. And when we're having the gamma rays, and they are a million of a meter. So even a million times smaller than light. But it's all electromagnetic radiation. The wave theory provided a very fruitful Young's experiment. Thomas Young in 1802, he proved an experiment that Isaac Newton was not completely right about what he said about light, but that it was it did. The development that disproved the corpuscular theory of light was the demonstration in 1802 by the Englishman Thomas Young that beams of light show interference, a characteristic of any form of wave motion. I cannot explain it because I don't know what interference is. Whatever, he showed that light moves as a wave. Okay, the wave theory proved very fruitful, Thomas Young's. Young's experiment, for example, led to the development of the diffraction grating. This is similar in concept to Young's original apparatus, but instead of 2 slits, has several thousands. Okay, I think I know what we're talking about. Let's read on. It can be used to determine with great accuracy the wavelength of each particular color and to separate out and identify the different colors in any beam of light. So I don't get it completely. Basically what we're doing is, I have no 2 ideas. First, we're doing something along a line like that. We're having a light and we're putting it through a very thin hole, and just the light comes through it with that wavelength. Or the other thing is we're having 1 or 2 or more holes in something, and now only some light passes through some. I don't get now what we get, but that is the setup of a whole experiment. Now we have to understand what we're actually doing there, but just so that you can follow. This is similar in concept to Young's original apparatus, but instead of 2 slits has several thousand. It can be used to determine with great accuracy the wavelength of each particular color and to separate out and identify the different colors in any beam of light. Okay, I don't understand it better. They're having light and making it through a hole in the paper, and some light comes through the small hole, other not, and it goes to one side or something like that. With this setup, we have not just to understand it, but we can imagine it. This process is called optical spectroscopy and is fundamental to many branches of scientific analysis. Okay, spectroscopy. I think we're going to explain that in that part, spectroscopy. The wave theory of light also explains the effect known as polarization. Normally, light vibrates in all directions at right angles to the direction of the wave. Just as a piece of string can be restricted to vibrations in a single plane by passing it through a narrow slit, so all the different vibrations of light, except for those in a single direction, can be eliminated by passing the light through a polarization filter. Okay, it seems to light moves in all directions, but if you have a hole, then all the light comes like that through it, all the light goes in all directions, but there only the light which happens to travel exactly on that line through that hole continues then on just on that line. So you have just here lamp burning, and it puts the light in all directions. Some going up and to the side, but some just happen to be just on that level. Some go here and some go here. And the one which passes here along that line will pass exactly through that hole and then continue straight on that line. They don't just start here to change their direction, just at the beginning. But they don't completely get it. But at least we have something to imagine. Just as a piece of string can be restricted to vibration in the single plane by passing it through a narrow slit, so all the different vibrations of light, except for those in a single direction, can be eliminated by passing the light through a polarizing filter. A second filter at right angle will then cut off the beam. This is the basis of Polaroid sunglasses, and instruments using polarized light are employed in both chemical and physical analysis. Okay, don't give it. But, okay. Light in modern physics, we don't have time left for it. That means that also physics part to light. We're going to continue in the next part with light in modern physics and then energy and photons, and then we're going to do this thing about the proof that light travels in waves also. That means if you're here for physics, you can go directly to the next part of physics. If you stay here and participate in the body center training, then it's very honest. We're having the legs standing shoulder width apart, hip width apart. We're going a bit down to the knees. Now flex the leg muscles and press them together. And now bend one leg. Flex the whole time and press together. Straighten the leg. Press together, flex, and back into the middle. Press together, flex, and straighten the other leg. Flex and press together. And bend again the leg. And up again. Now a bit wider apart the legs. Into the knees. Flex again all the leg muscles and press them together. And straighten again one leg. And bend again with the leg. Press together, flex the other leg. Straighten the leg and now bend again the knee, or bend the leg. And up again. Now the legs a bit closer together and press to the outside to get a good balance. Okay. One leg up now, into a right angle with the leg. A flexed foot, even aligned hips, taller with the back, and press from the top against the knee. Have a little bend in the other. And now press from the side. Now press up and to the side, a bolt block. And with the other leg, press from the top. From the side, slash and backslash exercise. And now again the bolt lock. Press up and to the side. And now the heavy swing door, one leg up, press from the side and up slowly. And close again. Other leg up, press from the side and up again. And close again. And down and low, 3 exercises on the ground. First the side plank, just on the elbow. You can do it also on the knees. And now if you can, and like one leg up. And now on the long arm. First standing, an arm out and the legs up, and pull knee to elbow. And one more. And over to the other side. First on the elbow. Then if you can, and like one leg up. And now on the long arm. One arm out, leg up and bring elbow to knee. And up again. Now walk a bit over the place. One leg, pull it up. Other leg, pull the leg up, point with the toes down, relax the leg, the mushroom, and the crane. Take the leg as the ankle, make a straight back, and point with the knee down to the ground. Other leg, take it at the ankle, straight back, knee down to the ground. Legs wide apart, and we're doing the trunk catalyst. Breathe in down, and breathe again out. Again in, and out and down. Breathe in and close the legs, and breathe again out. That was the body center training. I thank you very much, and until next time.